In the last few classes, we were discussing about Green's functions, path integrals, Feynman rules, etc. And now we are equipped with all the techniques and tools to deal with any interacting theory. So our aim is to calculate interactions in quantum electrodynamics, and for this we need some extra preparation, especially to describe fermions. Field theory for spin half particles called fermions are given by the Dirac equation. So it can be used to describe electrons and therefore it is very much useful. So let's see the Dirac theory. So we know that the Schrodinger equation is given by I partial t psi is equal to h psi, right? And it is first order in time derivative but is Lorentz covariant. Means that this equation has the same form when you go to a different frame. Therefore, this is Lorentz covariant. The form of the equation looks the same. That is, different observers in different laboratory see the same equation. In order for the Schrodinger equation to be covariant, the Hamiltonian h must be first order in spatial derivative. This must be first order in spatial derivatives. So which has a form h is equal to alpha minus I gradient operator plus m beta. Here m is the mass and this operator is the gradient operator okay, it represents the spatial derivatives and it is a vector with 3 components. It is a vector with 3 components. So at a glance, this equation does not make any sense, right? But if psi is ordinary function and alpha and beta are constant, okay, constants, then this gradient operator is not contracting with any other term. So that is an issue. Okay, if suppose if h is given by this equation, then I can rewrite the Schrodinger equation as I partial t psi is equal to minus I plus m beta psi. Okay, so here you can see that if psi is an ordinary function, if psi is an ordinary function, and alpha and beta are constants, then the gradient operator cannot contract with any other term. And this cannot be Lorentz covariant. If gradient operator cannot contract with any other term, contract in the sense you have del mu, then this will contract and this will be Lorentz invariant. But in this equation, psi is an ordinary function, alpha and beta are constants. If that is the case, then the gradient operator cannot contract with any other term, and therefore this equation will not be a Lorentz covariant. Right? This equation will not be Lorentz covariant. So it cannot even be rotationally invariant. That is also not possible. Rotational invariance is also not possible. Then Dirac had an idea that nobody thought about. That is, take alpha and beta to be, let alpha and beta to be n cross n matrices. Okay. Then, and also psi, let it be an n component vector. An n component vector. So if alpha and beta are n cross n matrices and psi is an n component vector, right? For Hamiltonian to be Hermitian, for Hamiltonian H to be Hermitian, alpha comma beta, there has to be Hermitian matrices, right? They have to be Hermitian matrices. So if you have a Lorentz covariant equation, its solution should have a relativistic plane wave equation. And the minimal requirement is that this equation should have a plane wave solution with standard relativistic dispersion relation. P square is equal to minus m square. But we know that the Klein-Gordon equation has such a solution, right? So we have seen that the Klein-Gordon equation has a plane wave solution with the dispersion relation p square is equal to minus m square. Okay. Since we cannot define a positive definite probability in Klein-Gordon equation, we will not take this, but instead we take the first equation, okay, this equation, Schrodinger equation, and then we square it. Okay, so if I square on the left hand side, I will get partial, second order partial, right? So I square will be minus 1, so minus partial t square psi will be equal to minus I plus beta m whole square psi, which is equal to minus alpha I alpha j, right, partial xi partial xj psi plus beta square m square psi. Then there will be cross terms. So first I have written this term as the first term square, right, and second term square is this term. Now I have to take the cross terms. So cross terms will be minus I, then beta alpha I plus alpha I beta, then m will be there and the partial derivative. So this will be the cross terms. So this cross terms appear as alpha comma beta are matrices, and it is not necessary that they commute. Okay, so alpha comma beta are matrices, and therefore it is not necessary that they commute each other, and therefore a cross term will appear. So we want the RHS of this equation to be similar to that of the Klein-Gordon equation, because Klein-Gordon equation has a plane wave solution and we also need a plane wave solution. Okay, so if you have a Lorentz covariant equation, its solution should be a relativistic plane wave equation. Therefore, the RHS has to be of the form, right? See, on the LHS I already have minus partial square psi. Okay, so on the right hand side I need spatial derivative, second order spatial derivative, right, plus m square psi. Then if you see, if I take this spatial derivative to the other side, then I will get partial square psi, which is equal to m square psi. So it will be of this form, which is the Klein-Gordon equation. So for this to happen, this must be equal to this. Okay, so I have to compare these two expressions. Okay, I'll compare the coefficients of psi, m square psi, and the partial derivatives, right, so that I can get the condition. What is the condition for this equation to be Lorentz covariant? Okay, so by comparing these two expressions, I get if I not equal to j, right, then the off diagonal elements must vanish, because you don't have any off diagonal elements, you have only xi term. So here you have xi xj, which means I equal to j is only present in the RHS. I not equal to j, that is off diagonal elements must vanish. Okay, and if I is equal to j, then you get partial xi square on the RHS. So this is required. Therefore, I can write the first condition will be alpha I alpha j plus alpha j alpha I must be 0. Okay, so you can see here, if you compare these two equations, right, then you can see that in the first term there is alpha I alpha j, right, there is alpha I alpha j, right, but here you have only xi's, which means if j is present, then the coefficient has to go to 0. So if j is present, alpha I alpha j, then the coefficient has to be 0. Okay, and next if I compare the second term, this term and this term, then beta square is equal to 1, or identity. Beta square is equal to identity. And also here you can see, if I is equal to j, then the coefficient is simply 1, which means alpha I alpha j, if I is equal to j, it is alpha I square. So alpha I square is also 1. So alpha I square is also 1 and beta square is also identity. Okay, therefore the second point is that alpha I square is equal to beta square is equal to identity. Okay, this is I equal to, from I equal to j, and this is from I not equal to j, right? And similarly you can see here there are only two terms, first term and second term. So here there is a third term present. This third term must vanish, for which this bracket beta alpha I plus alpha I beta must be 0. Therefore, the third condition says that beta alpha I plus alpha I beta must be equal to 0. Okay. And the final one we have already discussed, alpha and beta must be Hermitian. Hermitian means alpha I dagger must be equal to alpha I and beta dagger is equal to beta. So alpha and beta are Hermitian matrices. If all these four conditions are satisfied, we can have plane wave solution. So try to find the matrices that satisfies these conditions. So we already said that a constant matrix will not work, right, as it is a constant, right? We have already said that a 1 cross 1 matrix will not work, right? 1 cross 1 matrix in the sense it is a constant. If alpha or beta is a 1 cross 1 matrix, which means that it is a constant or it is a scalar quantity. And we have already seen that if alpha, beta are constant, then it cannot contract with any other term, right? The gradient operator cannot contract with alpha or beta because it is constant and the equation will not be Lorentz covariant. Therefore, alpha and beta cannot be constant. So it cannot be 1 cross 1 matrix also. It has to be a matrix, but it should not be a 1 cross 1 matrix because 1 cross 1 matrix means it is a constant, right? So we can start checking with 2 cross 2 matrix, then 3 cross 3, etc. But still we can see that they won't work. So you need at least a 4 cross 4 matrix to satisfy all these four properties. Okay, that is n is equal to 4. That is the minimum requirement. You need a 4 cross 4 matrix to satisfy all these properties. So what is the solution? So there are infinite number of solutions. There are infinite number of matrices possible for alpha and beta. Okay, I'll just mention two. The first solution is beta is equal to a 2 cross 2 identity matrix 0, 0, minus and alpha I is equal to 0, sigma I 0. So here sigma I, the sigma are the polymatrices. Okay, sigma are the polymatrices. So this alpha and beta satisfies all the four conditions that we have mentioned here. Okay. And another solution is given by beta is equal to 0, 2 cross 2 identity matrix and 0. Also alpha I is equal to sigma I 0, 0 and minus sigma I. So this is second solution. Okay, and likewise there are infinite number of solution possible for alpha and beta that satisfies these four conditions. Okay, so alpha and beta are 4 cross 4 matrices, right, which implies psi must be a 4 component vector. Okay, something like psi is equal to psi 1, psi 2, psi 3, psi 4. 4 component vector. Okay, in general I can represent psi alpha with alpha equal to 1, 2, 3 and 4. Okay, and this can be a complex vector. Okay, this new object is called a spinner. This new object is called a spinner, as they describe spin half particle. Okay, it describes spin half particles. Okay, so I can rewrite the Schrodinger equation. This is equal to minus I alpha plus beta m psi. So this is a matrix equation. Right? So psi is spinner and alpha and beta are for minimum it has to be a 4 cross 4 matrix, and it can have many solutions. And for convenience, let's change the form of this equation. Okay, so I want to change the form of this equation. So first I'll multiply it with beta on both sides. Okay, so I do this for changing the notation. So let me multiply beta on both sides. So I beta partial t psi is equal to minus I beta plus beta square, already there is one beta, m psi. And one of the properties says that beta square is identity, therefore I can write beta square is equal to 1. Fine. Now I substitute minus I beta, then instead of alpha in this form, I'll write it in this form, partial psi plus m psi. Okay, and I beta alpha I am just giving another notation, gamma I, and on the left hand side I have I beta, okay, which I am representing by gamma 0. Okay, so gamma I is equal to I beta alpha I, and gamma 0 is equal to I beta. So I can rewrite the above equation as gamma 0 partial t psi is equal to minus gamma I partial xi psi plus m psi. So I can combine these two and write gamma mu. So mu can be 0, 1, 2, 3, and this is I. So I am combining these two as gamma mu del mu. Okay, so 0 means it's time derivative and this will be spatial derivative. Minus m psi, because this m when it comes to the other side it will be minus. So this will be equal to 0. Okay. So this metric equation can be represented in the component form. So if gamma mu is a matrix, then its component can be written as alpha beta, right? Then partial mu psi beta, because psi also has components, minus m psi alpha is equal to 0. This is the component form of the equation. And you can see that here beta and mu are summed over. Beta, beta, right? So beta and mu are summed over. For fermions, you have to deal with the gamma matrices. Therefore, the conditions 1 to 3, okay, can be written. These has to be written in terms of gamma matrices, because for fermions you always have to deal with gamma matrices. Fine. So I'll rewrite all the conditions in terms of gamma. So I'll write gamma mu plus gamma nu gamma mu is equal to 0 for mu not equal to nu. And gamma 0 square is equal to -1, and gamma I square is equal to 1. And these two conditions can be represented in a more general form. Okay, I can write gamma mu gamma nu commutator is equal to 2 eta mu nu. Okay, so when mu is not equal to nu, then the RHS will be 0. So you'll get gamma mu gamma nu plus gamma nu gamma mu is equal to 0, which is the first condition. And similarly, for mu equal to nu, I'll get gamma mu plus gamma mu is equal to 2 eta mu mu. So what is eta? You will get -1, 1. So this is eta, right? This is eta. So when mu is equal to nu, then you will be having all the diagonal terms. So if mu equal to nu equal to 0, then I'll have eta 0 0 is equal to -1. Then gamma 0 square plus gamma 0 square is equal to 2 times -1. So 2 is equal to -2. So gamma 0 square is equal to -1. So that was our second condition. And similarly, if mu is equal to nu is equal to I, then eta I is 1. The other diagonal terms are 1. Therefore, I will get 2 gamma I square is equal to 2. So gamma I square is equal to 1. So in general, I can represent it by the anti-commutator, right? The anti-commutator gamma mu gamma nu is equal to 2 eta mu nu. So any set of gamma mu satisfying this anti-commutator equation is called a representation of Clifford algebra. Okay. And finally, we have to change the notation of the fourth condition. So what was the fourth condition? The Hermitian matrices, right? Alpha I dagger is equal to alpha I and beta dagger is equal to beta, which means that alpha and beta are Hermitian. Similarly, you have to write the Hermitian condition for gamma also. So the final condition, I will write gamma 0 dagger is equal to minus gamma 0 and gamma I dagger is equal to gamma I. So from where did this come from? I substituted for gamma 0. So when gamma 0 dagger, if you want to find out what is gamma 0 is I beta. So I beta dagger. So I will become minus I, and beta dagger is beta itself, right? So minus I beta, which is minus gamma 0, right? So that's how I got it. Similarly, I can do for gamma I dagger also. So you'll get gamma I because there is already a minus there. Fine. So these two in general I can represent by gamma mu dagger is equal to gamma 0 gamma mu gamma 0. Okay, this is also an important property or the important condition, fourth condition. Okay, now what is this gamma matrix? So we have already defined what is gamma. From here, gamma I is I beta alpha I and gamma 0 is I beta. So I have already told you that alpha and beta will have infinite number of solutions. So infinite number of matrices is possible for alpha and beta, but I explained only two solutions. So according to those two solutions, you can have again two solution for gamma also, right? So corresponding to solution number 1, I can write gamma 0 is equal to I 0 0 minus I, right? And similarly I can have gamma I. So this is a 4 cross 4 matrix. Okay, so when I say I, it is I multiplied by identity 2 cross 2, okay, and minus I, and here gamma I is equal to 0 I sigma I minus I sigma I 0. This is corresponding to the solution number 1, and corresponding to the solution number 2, I can have gamma 0 I 0 and gamma I is equal to 0 minus I sigma I sigma I 0. Okay. So corresponding to solution 1 and solution 2, you can have two different gamma. Actually they are all equivalent, but they are all the solutions for the equation, and we'll see. Let's go deeper into some insights, so you'll get why there are infinite number of solutions and which one you can consider, or are all of them equivalent or not. Let's go deeper into some of the insights. Okay. So when m is equal to 0, right, that is the massless Klein-Gordon equation will give a dispersion relation p square is equal to 0. Otherwise p square was equal to minus m square, but when m is equal to 0, the massless Klein-Gordon equation will give a dispersion relation p square equal to 0. And correspondingly, the Schrodinger equation I partial t psi is equal to minus I alpha I partial psi, right, and plus m square term will not be there because m is equal to 0. So only the first term will be there. Okay, so this will be the equation in the massless case. Now you will get alpha I comma alpha j commutator anti-commutator is equal to 0 I not equal to j. Okay, this is known case, and alpha I square is equal to 1. So these are the conditions, because if there is no mass, then there is no need of beta. So you will have only the conditions in terms of alpha. Okay, then the solution will be different. Then what will be alpha? If there are only these two conditions, then there is only one group of matrices that anti-commute with itself, right, and whose square is equal to identity, and they are called as the polymatrices, which means that alpha I will be equal to sigma I when there is no mass. So when m is equal to 0, then alpha I is simply sigma I. So this result tells you something important. The equation for a massless particle and a massive particle are very different. Massive particle needs 4 components, right? So we have seen 4 cross 4 matrix. So the massive component needs 4 cross 4 matrix, and the corresponding psi is a 4 component vector, right? So psi 1, psi 2, psi 3, psi 4. But in the case of a massless particle, it can be described by a sigma matrix, which is 2 cross 2. Okay, and therefore the psi for a massless particle can be described using a 2 component vector, psi 1, psi 2, and they are all complex. Okay, so this tells us that massive particle has more degree of freedom than the massless particle, right? And secondly, from the Dirac equation, we can derive an equation for conserved current. Partial mu J mu is equal to 0. Okay, where the 0th component of the current J0 will be a positive definite quantity classically, right? This will be positive definite quantity classically. Okay, so from the Dirac equation we can derive an equation for the conserved current such that the 0th component J0 will be a positive definite quantity classically. Fine. And the third insight about Dirac equation is that we can have infinite number of solution for the matrices alpha and beta that we have already seen. We discussed only 2 solutions. And what is the meaning of this solution? To understand this, you have to consider a basis change in psi. So we know that psi is a basis. So if you change the basis psi to psi prime such that psi prime is equal to some constant b times psi. Okay, here b is complex, constant, invertible matrix. Okay, so inverse exists, invertible matrix. Okay, so complex, constant, invertible matrix. Okay, so psi, so you are doing a basis change from psi to psi prime such that psi prime is equal to b psi, and if it satisfies, right, if psi satisfies the Dirac equation gamma mu del mu minus m times psi is equal to 0, then psi prime must satisfy gamma mu prime del mu minus m psi prime is equal to 0, right? If the basis changes, then if psi, the basis changes from psi to psi prime and psi satisfies this equation, then psi prime must satisfy this equation. Okay. And the relation between gamma mu and gamma mu prime will be gamma mu prime is equal to b gamma mu b inverse. Okay, So we can do basis transformation, but it should not change the physics. Therefore, the set of gamma mu related by a similarity transformation are equivalent, right? So they have to be equivalent, otherwise the physics will change. So for any basis transformation, the transformation should not change the physics, and therefore sets of gamma mu related by, what is this? This is a similarity transformation. By a similarity transformation are equivalent. So under such equivalent relation, the representation of the Schrodinger equation is unique. Okay, any matrices that satisfy the Schrodinger equation are all related by similarity transformation, and all the solutions are physically equivalent and corresponds to change of basis. All the solution are physically equivalent and corresponds to change of basis. So the different forms of gamma matrices may be useful for different purposes, right? So the solution 1 that we have discussed is convenient for non-relativistic limit. And the solution 2 that we have discussed is convenient for the opposite regime, which is called as the ultra relativistic limit. Okay, so both 1 and 2 are equivalent, right? And it just corresponds to change of basis. So all the solutions are physically equivalent and corresponds to change of basis, and according to our convenience and situation, you can choose which solution to use. So in order to show that Dirac equation is covariant, we have to make Lorentz transform and show that Dirac equations are same in every Lorentz frame. So that we'll do it in the next class. Okay. So for today we'll stop here.